So which line do we want to use, right? Where do we want to put the 4 lines coming in? We've got, just a little union here, 2 3-way valves, and we have 4 lines. Do I want to put the oxygen and the hydrogen on the same pair, or do I want to put them on different pairs? Same. Why?
So that if the valve is damaged, then oxygen will never get much higher.
Yeah, this 3-way valve prevents me from mixing 2 things together. It's saying you're either flowing hydrogen or oxygen. I can't flow hydrogen and oxygen at the same time by accident. Now, if the valve's malfunctioning, oh well, I'm in trouble. So it actually doesn't help that much with valve malfunction, but it's about as good as I can do within the budget I have for worrying about safety. But at least this prevents human error, right? Hey, it's expensive to get valves that literally never fail. That's not a cheap thing to do. You have to have multiple fail-safes in place. But I can avoid the human error really easily. Because it's real easy for somebody to turn the wrong valve and suddenly you're mixing hydrogen and oxygen at 500 Celsius and boom. Yeah. So I learned on Tuesday, part of the reason I was late, is we have, so for this class, the ABET accreditation thing, I have to teach you guys something about safety. So it'll be something about reactors blowing up or something like that. We have to design a problem specifically to focus on, they're called SLOs, learning objectives. And there's 2 for this class. I can't remember one of them, but one of them is process safety. Okay, so now we're going to look at heat transfer to reactors. So I have a CSTR. Does it operate at a range of temperatures or one temperature? One temperature. Just like it operates at one conversion and one concentration, it's one temperature because I have that impeller and it's mixing everything up, and we're just assuming that the temperature is constant throughout the entire vessel. Of course, it's not in reality, but it's the assumption we make in a class like this. And now we have some outlet flow where we have whatever is not reacted of A, some temperature, and some conversion. And remember, that's the same as the inlet. Or sorry, the same as what's happening inside. The inlets, though, are different. And so in addition to these streams, I have this, we'll say cooling, but understand that it could be heating too. So some sort of heating or cooling jacket. And so I have an inlet temperature here. And some outlet temperature there. And I'm flowing through some sort of heat exchanging liquid. You can think of antifreeze if it helps you. But you're flowing some sort of liquid in that will absorb heat from the system or give heat to the system. So Q, is it the rate of heat into or out of the reactor?
It's cool. It's out.
Careful. Q is defined.
Oh,
Negative or positive might change the direction of heat transport. But if Q is just Q, in other words, if Q is greater than 0, where's the heat flowing? Into or out of?
out.
Into. So remember from the energy balance that I put up at the start. Q is heat transport into heat flow into reactor. So a little bit of review from your heat transfer class. Try to match the notes. So U is what?
Overall heat transfer.
Yep. Which has units of something like watts per meter squared Kelvin. What's area? Sorry, what's A? But which area is it?
Where the surface is.
Let's just say more generically, it's the heat transfer area. And theta m, which is in the first but not the second equation, everybody remember what theta m is? Yeah, say it louder and like not like you're in a hurry.
Log mean temperature. Had to be air to it.
It's the logarithmic mean of the delta T. Okay, so any questions about any of these terms? This is the heat transfer fluid in, out. This is the temperature of the CSTR, right? Yeah.
Those don't, doesn't theta m depend on whether it's cross flow or counter flow?
Not when temperature is constant.
Right.
You're thinking of a heat exchanger, and we will have those problems later. Temperature's constant in the middle, right? So,
Right.
but yes, if I had a PFR, it would depend on it, and we're just not there yet. Okay, so let's do an energy balance, not on the reactor, but on what?
Water.
Water, if it's water, but the heat transfer fluid, right? So MC, the mass flow rate. Of that heat transfer fluid. Heat capacity of that fluid. Inlet minus outlet temperature plus what? Energy balance, right? So this is the flow in and out. What term am I missing? Is there a shaft term? No. Is there accumulation? No. So what term am I missing? Q. Do I put Q in like this? No. Why not? It's negative Q. Why is it negative Q?
It's heat flow into the.
Right, because Q is defined as heat flow into the reactor, so it's minus Q. So don't trick yourself up by having Q be into the heat transfer liquid in some of your equations and Q be into the reactor in some of your other equations. Right? Q is Q. It's always into the reactor. If you're using it anywhere else, make sure the sign matches. Yeah.
In this situation, we're assuming no phase change.
Yeah. I mean, that's why.
I mean, like, I didn't know if we wanted that.
Yeah, it's not in these notes. Hopefully we don't have to deal with forming steam on the outside. We probably will, but yeah, if you just have it going in at one temperature, not the other, without phase change, this is what you get. Okay, and then we have Q, this equation. So let's use that, and we're going to substitute that into there. So through rearrangement, you guys can see that Q is equal to this, right? I'm not going to leave everybody behind in a second. So I can set that Q equal to this stuff. So does anything simplify?
Yeah, it's good.
So if we look at it after things have canceled, what's unknown up here? Are we going to know the heat transfer coefficient or be given it? Area, mass flow rate, and heat capacity of my cooling fluid?
You don't know the temperature of it.
Right, no, it's a good point. I could either ask you for the temperature or I could ask you for the mass flow rate, right? But the point is that we're generally going to know one or the other of these. If you don't know either, you're kind of stuck. I have to tell you something. I can't ask you for the outlet temperature if I don't tell you the mass flow rate of the cooling fluid. So other things, though, that you could be asked for, you could be asked for the temperature coming out of the cooling fluid. So that's what we'll define first. So this is the outlet temperature of my cooling fluid. This is the temperature of my reactor.